What does E raised to a matrix even mean? Well, take the Taylor series for e to the x, replace every x with a matrix A, and you get an infinite sum of matrices. Remarkably, that sum always converges, and it's the single most important object in linear differential equations, the matrix exponential, e to the at. Let's start where we can see it clearly, the scalar case. The equation du dt equals times u has the solution u of t equals e to the at times u of 0. One number a, one exponential, and we're done. Now let's promote u to a vector and promote a to a matrix A. The system du dt equals a times u couples the components together. The matrix A mixes u1 and u2. We want the matrix analog of that clean exponential solution. Our guess is u of t equals e to the at times u of 0. Our job now is to define what e to the at actually means and then prove that it really does solve the system. The trick is to change bases. Let S be the eigenvector matrix of A. Its columns are the eigenvectors. And then let capital lambda be the diagonal matrix of eigenvalues. If A has n independent eigenvectors, then A equals S lambda S inverse. Now substitute U equals SV, then du dt equals S times dv dt, and AU equals ASV. Setting these equal gives S times dv dt equals ASV. Multiply both sides on the left by S inverse. That gives dv dt equals S inverse AS times V, which equals lambda V. Look what happened. The coupled system in U became a diagonal system in V. Each component evolves on its own. dv1 dt equals lambda 1 times V1, dv2 dt equals lambda 2 times V2, and so on. We've turned one coupled matrix problem into an independent scalar problems. That is the entire philosophy of diagonalization in one line. Each scalar equation has a simple scalar solution, v sub I of t equals e to the lambda it times v sub I of 0. Now stack those scalar solutions back into a vector. We get v of t equals e to the capital lambda t times v of 0, where e to the capital lambda t is the diagonal matrix whose diagonal entries are e to the lambda 1t, e to the lambda 2t, and so on, down to e to the lambda nt. Now we transform back to the original variable. Since u equals sv, we have u of t equals s times e to the capital lambda t times v of 0. Right? And from u equals sv at time 0, we get v of 0 equals s inverse times u of 0. Putting it all together, u of t equals s times e to the capital lambda t times s inverse times u of 0. The operator sandwiched between the initial state and the future state is what we call e to the at. So for a diagonalizable matrix A, e to the at equals s times e to the capital lambda t times s inverse, clean, computable, and built entirely from scalar exponentials. But we need a definition that doesn't depend on diagonalization. Here it is. E to the at equals the identity matrix plus a times t plus at squared over 2 factorial plus at cubed over 3 factorial, and so on forever. The series converges for every matrix A and every time t. The factorials in the denominators grow so fast that they crush any growth in the numerator, no matter how large the entries of A are. Let's do a quick sanity check. Take A equal to the diagonal matrix with entries 1 and 2 and set t equal to 1. The first term is the identity, diagonal 1, 1. The second term, at, is diagonal 1, 2. The third term, at squared over 2 factorial, is diagonal 1 half and 2. Adding these three gives diagonal 2.5 and 5. And if we kept going, the sum would head toward diagonal e and e squared, which is about 2.718 and 7.389. We have the formula. Now let's see why it works term by term. First, compute a squared, that's s lambda s inverse times s lambda s inverse. Look at the middle, s inverse times s collapses to the identity, and the identity just disappears. What's left is S lambda squared S inverse, the same cancellation telescopes all the way up. For any power, NA to the N equals S lambda to the N S inverse. Now plug that into the series for e to the AT. Every single term has an S sitting on the far left and an S inverse on the far right, so we can factor them out of the whole sum. What remains sandwiched in the middle is the sum of lambda to the n times t to the n over n factorial, and that's exactly the definition of e to the lambda dt. So the series definition and the sandwich formula agree. E to the at equals s times e to the lambda t times s inverse. Why is e to the lambda t so easy to compute? Because lambda is diagonal. When you raise a diagonal matrix to the nth power, you simply raise each diagonal entry to the nth power. So lambda to the n has lambda 1 to the n, lambda 2 to the n, and so on down the diagonal. That means the power series on each diagonal slot is exactly the scalar Taylor series for e to the lambda, GD times t. Putting it together, e to the lambda t is the diagonal matrix whose entries are e to the lambda 1t, e to the lambda 2t, and so on. For a concrete example, if lambda equals the diagonal matrix with 2 and minus 1 on the diagonal, then e to the lambda t is the diagonal matrix with e to the 2t and e to the minus t on the diagonal. Now a quick warning. Don't confuse the matrix exponential e to the at with another matrix series you may have seen. The geometric series, capital Y plus at squared plus at cubed, and so on, with no factorials in the denominators, sums to the inverse of the quantity I minus at. It looks almost identical to the exponential, but the difference is crucial. Without factorials, the terms can blow up. This geometric series converges only when every eigenvalue of at has magnitude less than 1. By contrast, e to the at converges for every matrix A and every time t. The factorials save us because n factorial grows faster than any power. Still, the two series do agree to first order. Both begin with I plus at. So for small t, the inverse of I minus at is a good approximation to e to the at, and that's exactly why implicit ODE methods use it. But make no mistake, they are not the same object. One more caveat, the formula e to the at equals s times e to the lambda t times s inverse requires s to be invertible. That means A must have n independent eigenvectors. If A is defective, lacking a full eigenbasis, then S inverse doesn't exist and the shortcut fails. But the series definition still works. Every matrix, diagonalizable or not, has a matrix exponential. For defective matrices, you use Jordan form or just sum the series directly. The object always exists, only the computational shortcut is conditional. Let's zoom out. E to the at is the propagator of linear dynamics. Feed it an initial state u of 0 and it hands back the state at time t. Its behavior is controlled entirely by the eigenvalues of A. If the real part of lambda is negative, e to the lambda t decays and that mode dies out. If the real part is positive, it blows up. If lambda is purely imaginary, e to the lambda t oscillates on the unit circle. Stability is eigenvalue sign, period. This one object underlies control theory, Markov chains, and the quantum mechanics, where the Schrödinger evolution is e to the minus iht. Here is the big idea. Diagonalization turns one couple matrix problem into n independent scalar problems, and the matrix exponential is the cleanest expression of that philosophy. Raising a number to an exponent is easy. Raising a matrix to an exponent means diagonalize, exponentiate the eigenvalues, then rotate back. Same idea, just a bigger canvas.